Okay, everyone. Let's get going. Jonathan, if you're ready, can you?
Hey, sure. One second here. All right. I'm going to go ahead and share my screen here. Can everybody see this?
Yep, I can.
Yep, looks good.
All right, awesome. Okay, so rather than just going through the slides that we have all presumably watched, which I mean, honestly, so this is just an experiment because I'm definitely not an expert here, and I mean, presumably none of us are experts in this stuff. Otherwise, we probably wouldn't be taking the class. But with that said, I wanted to, just kind of for the sake of organizing this in my own brain, try and set this presentation up a little bit separately. So I basically drew from a whole bunch of different sources, which I will compile and post. So this is a bit of a hodgepodge, but I believe I've got it organized pretty well. So we'll see how this goes. This is just just a test. If nobody likes it, next time I'll just go back to the slides. But yeah, so just looking for feedback, and if you guys like it, cool. If not, that's cool too, and I can just jump right back over to what we would normally be doing. So this first part is just going to be the introduction to flows, right? So this goes up through everything right before he jumps into the inverse autoregressive and autoregressive flows. So the point here is just to kind of get a foundation for what are flows, what's going on under the hood for these flow models before we get into the nifty architectures that people have actually built using this. If it will actually go. There we go. So first thing I wanted to do is kind of put it in context, right? So flow models versus a bunch of other generative architectures. So I mean, we've gone through these autoregressive ones, and really some of these distinctions are a little bit false because you really can combine different components from all of these different columns. And as we see, like we actually will be talking about autoregressive flows. So it's kind of a combination of both of these. But I do think it's helpful to kind of parse this out in a distinct sort of way. So yeah, basically I've got this table up here. So we're looking at like four different classes of models. And this obviously isn't comprehensive. Like I don't have like energy models up here, for example, right? But these are probably the four big ones that we're going to be going over anyway, right? So autoregressive, flow, variational autoencoder, VAE, and then the generative adversarial networks, or the GANs, right? And then on the rows, I've got some desirable properties we like. So for one, I mean, if we're doing generative architectures, we want to have exact sampling, right? Which is to say, if I put in if I sample from some latent space or do sampling somehow and run this through the architecture, I want to be able to get an exact sample that corresponds to that input, right? And all of these do that. These are generative architectures by their nature. So that's cool. But then what do I mean by exact inference? What I mean by exact inference is if I was to take an example, so a single X example, and push it through this architecture, is there a way I can get a probability on the other side? So can I get P of X out of this thing? And for the autoregressive models, we saw, yes, that's perfectly possible, just by design. That's how we've set it up. And for flow models, we can do this as well. VAEs and GANs, that's not really as straightforward, right? I mean, if you take a look down at this little diagram, I found this on a cool little blog. You can see with the GAN, you're not actually learning that P of X explicitly. It's sort of implicit. You're essentially training this generator or training this discriminator, whichever you're using it for. But that's allowing you to go from your Z space to your X space, but there's not necessarily a way to go from your X space back to your Z, right? So there's not necessarily a way to map that X to some probability. And the same goes for the VAE. You might look at the VAE and say, well, it looks like you could do that. But it turns out, and once again, my understanding of VAEs is very limited, possibly a little bit fallacious. So take what I say here with a grain of salt, but my understanding is that VAE is going to, as per the standard autoencoder, it's basically boiling it down to some potentially smaller latent space. So that encoder is, it's basically an approximation, right? So it's taking X and it's trying to compress it down to this, this latent representation. And then it uses this decoder to try and bring it back out into the X space. But this is not an exact process, right? So you don't exactly get a P of X for any particular Z here. So I'm a little bit, I'm not super certain on this one. If anybody knows more about this, feel free to jump in. Honestly, I'm really cool with this being a discussion. So if anybody has any thoughts, just jump in and let me know. But yeah, I'm under the impression that you're not able to get an exact, probability density value for say some Z there, or sorry, for some X. You can't go from X and then find, okay, well, this is, P of X. Then we get to the flow-based models, and well, that's built into it. It is exact, right? It takes this distribution over Z and moves it to X, and likewise, you can go from X to Z. So for any given sample X, I can map that exactly into that Z space, and I can get some probability, right? And then these other categories, we want meaningful latent spaces. What do I mean when I say meaningful latent space? I mean, so this would be something that I guess it really depends on what you want to use it for, but I'm kind of thinking something where you can get some information, some useful information out of that latent space, or you can do something useful with it. Kind of like that glow example, if you guys got far enough to see that, where you can figure out, oh, well, this direction corresponds to smiling, or this direction corresponds to age, right? And you can figure out where that is in the Z space, and you can actually use that to do interesting things. You can learn interesting things about those latent representations. You can poke it and prod it, right? Autoregressive models, we don't have that. Yeah, there's not a way to directly access that latent space. But for flows, VAEs, and GANs, yes, we do have ways to probe them. But then also we want to be able to work with non-discrete data, so like continuous X space. And the autoregressive models, as we saw, were not capable of doing that, whereas these flows, VAs, and GANs can. So this is just sort of a quick summary of high-level properties for all of these different architectures. And so I know that was possibly a fair bit. Did that make sense? Did that resonate?
Yeah, I thought it was good. Very,
Okay.
good overview.
Okay, cool. Yeah.
Yeah, good summary.
Yeah, so ideally we want to have all the above properties. So we want exact sampling, we want to be able to generate new samples, we want to be able to figure out for a given sample what its probability density is, we want to have a meaningful latent space that we can poke and prod and do cool things with. And we also want to be able to work with continuous X's, not just discrete X's. But also we remember from that very first lecture, there's a few other properties we'd like. We want to be able to do all of this efficiently. And when I say efficiently, I mean, not only in terms of, say, compute resources, but time and also data. Like we'd like to be able to use the minimal amount of compute, minimal amount of time, and minimal amount of data to get some very high quality or some particular quality of representation. We also want it to be very expressive, right? Like linear regression is not terribly expressive by its nature. It's linear. It's assuming everything is linear. Likewise, many of these architectures we've seen, there's kind of this trade-off between the constraints that you bake in and the expressiveness that you can get out. But what I mean by the expressiveness then is for some particular architecture, what all can we learn? And I guess the maximal version of this would be something that has universality, right? Where we can literally approximate any function. So we want efficiency. We want to be able to do this with as little compute time and data as possible. We also want to be as expressive as we possibly can. And then finally, we also want it to be generalizable and robust, which is to say, if we move into slightly different domains or slightly different parts of the domain, we really don't want this thing to break. We want it to have a robust representation, something that's actually meaningful. Getting back to the potentially mythical what is that? I've heard it with tanks. I've heard it with like wolves and forests, but that whole idea that, what is this thing actually focusing on? Is it just picking up on the fact that wolves are, in mountains with snow and dogs are playing in grass, or, and it learns to differentiate mountains and snow versus, grass, when it's like you want it to actually differentiate dogs from wolves. So same kind of idea. We want the representations to be robust, and the more robust they are, the more generalizable this thing's going to be, and the less likely it is to just kind of go sideways in deployment. So, all right. So that said, let's jump into the intuition behind normalizing flows. So let's think about, what is it that makes a distribution easy to sample from, right? Well, the first thing would be, we want to be analytic. We want to be able to write something down that describes this distribution. We want to be able to like put down a comprehensible expression for it. But at the same time, we want that expression to be easy to evaluate. Anybody who's done Bayesian statistics knows that you can get some very intractable integrals, and you've got to use like Monte Carlo or one of those many different sampling techniques to approximate the integral, right? So just because you can write it down doesn't mean that you can evaluate it easily. But if you can't even write it down in the first place, well, then you're kind of out of luck, right? So you want to be able to write it down, you want to be able to evaluate it easily. And some prime examples of this would be like Gaussians and uniforms. Those are well-known, well-studied distributions that we can sample from very easily. Now, the underlying distribution for a given data set, well, first of all, it's probably unknown. Maybe you have used a synthetic data generation process, in which case you would actually have an idea about the underlying distribution. But generally speaking, if someone hands you a stack of images or a stack of text or any of the other sorts of non-traditional, non-tabular data we tend to work with, that underlying distribution for that is probably going to be unknown. It's also probably going to be complex, right? But there is something we know. We do know that for all valid probability distributions, P of X is going to be greater than or equal to 0 for all X in the sample space. Oh, sorry, that should be less than or equal to 1. P of X should be less than or equal to 1 for all X in the sample space. And then over that entire space, we should be able to integrate, sum up, what have you, all of these probabilities, integrate over the whole probability density to get 1. So, basically this distribution is normalized. It's got some fixed amount of probability mass spread out over this space. So whether we're talking about a very easy to sample from distribution like a Gaussian or a uniform, or a very complex distribution that describes our data set that's unknown, no matter what, if it's a valid probability distribution, it has to satisfy these properties. And so this is the idea behind these normalizing flows. Can we start with a very easy, already normalized distribution and transform it into a more complex one that describes our data? And, here's where the term comes from, normalizing flows. Normalizing in the sense that we're basically ensuring that what we end up with is a normalized distribution. Flows in the sense that we're transforming, we're going through the sequence of differentiable invertible transformations to move from one to the other. So normalizing flows. So actually, in the normalizing part, I actually think there's been some confusion. I think some people think normalizing has to do with being like standard normal or something. And I don't believe it has to do with standard normal. It has to do with the fact that, this distribution is normalized, and we're ensuring that after doing these sequence of transformations, we still have something normalized. Right? That was actually something that was that tripped me up a little bit at first. I was like, oh, okay, I see where that's going. So before we jump off into how to do this, though, first of all, I'm going to stop and say, anybody have any questions so far? I don't want to lose anybody along the way. I'm pretty bad about getting distracted during talks. So after 3, 4, 5 minutes of someone rambling, I'll kind of start to fade off, and then I'll miss something. I'll be like, oh, wait, hold on, where are we? So just checking in case anybody like me is falling a little bit behind. So if you have any questions, really honestly, just jump in and say something.
Does normalized mean the summation property, like where you integrate over it and it becomes 1? Is that what normalization?
Right. So when we're saying, so when we're saying normalize, what we mean is, that if we integrate over that distribution, we're going to get 1. So that's that third property. Yeah.
Okay. All right.
Yep. Cool. Thanks.
Cool.
All righty. So a quick refresher on probability density functions and cumulative density functions. You'll probably recognize some of these slides. Some of these I have shamelessly ripped and put in here, though I'm trying my best to keep track of credit for not only images, but content down at the bottom of the slides. So yeah, so what we have here is a probability density function, right? So you've got P of X on the left, you've got X on the bottom. So that is not actually a probability. If you go to say 0.8 and you go up to the top and it looks like that's 4, well, clearly that's not a probability, right? Because probabilities are between 0 and 1. So what is P of X? What is that thing? Anybody care to offer an opinion? What is P of X?
It's the probability mass between or X minus delta to X plus delta, some kind of very small.
Well, okay, so yeah, so you get into the equation we've got on the right there, right? So that's for the probability. So the probability involves integrating, right? So if you look at 0.8 and you go up to 4, 4 is not the probability. That's a probability density. It's a, sorry, my dog is having nightmares. Apparently she does not like PDFs. Stop. Anyway, if you hear the yipping and barking in the background, she's dreaming. Anyway, yeah. So at 0.8, you go up to 4. So that's a density. So that's effectively that's essentially a relative measure of how much mass is there. So what is density? Density is mass per unit volume, right? And of course, we're working in one-dimensional space here. So that would be mass per unit length, right? So this is a measure of the relative concentration of the probability mass, right? So there's a lot of probability mass concentrated around 0.8 and concentrated around that smaller mode around 0.3, and significantly less so around 1, 0, and 0.6. But how do you turn a density into a mass? Well, if it's mass per unit volume, then you have to multiply mass per volume times volume to get mass. So that's what the probability is. The probability is the mass. So by integrating from some point A to B, so start at one point in the distribution, go to the right to some other point, then you're effectively summing up all of the mass in that region, right? And so then that's where you get the probability. So yeah, so the PDF key point is not actually telling you what the probability is, it's telling you the probability density. And then that equation we see on the right there is how we actually get probability out of it. Okay. So, all right, so we have a probability density function on the left, and now on the right, we have a CDF. Now, what is the CDF? Well, the CDF is basically telling us the probability of observing some value X less than or equal to the current value. So let me say that again. Let me try that again. It's giving us the probability of some particular value less than or equal to the value we're looking at, right? So like, let's just choose a point X, somewhere between 0 and 1 here. So let's say maybe at 0.2. Well, then what the CDF is telling us is what is the probability that if I were to sample from this, I'm going to get something whose value is less than 0.2. And so if we go from 0.2 and we shoot up to the line, then we can then go over to the y-axis. And I wish you could actually see. Can you see my cursor now?
Yes.
Yes.
Oh, cool. Okay, good. That'll be much more helpful. I was like, man, I need to be able to point to things. So if we start with 0.2, then what the CDF is telling us is the probability, start at 0.2, go up to this, shoot over to the vertical axis, and that's going to tell us the probability that some sample value is going to be less than or equal to 0.2. And go over to 0.4, you can shoot up and likewise map over. So what this thing is doing is it's telling us, once again, it's saying what is the probability that for some X, what is the probability? I think I had it and then I tripped myself up here. What is the probability that some sampled value will be less than or equal to some x? How about that? So go to 0.6, shoot up. There's a flat region right here. So interestingly, it doesn't change too much in this region, which you can see like 0.5 to maybe 0.7. If we go over to the actual PDF, you can see why the probability doesn't really change too much. Like the probability of sampling a value less than or equal to 0.6 really isn't all that different than for say 0.7 or for 0.5. Right? Because there's a very little probability mass here. So not many values are coming from this region. But yeah. So coming out of an applied stats background, I'm a little bit more familiar with this stuff. And so I don't know where everybody else is on the spectrum with this. So if there's any more questions, I just remember the first time I looked at like CDFs, I was very confused. So if anybody has any questions on this, feel free to shoot. Anyone?
Yep.
Cool. All right. So let's keep on with the CDFs. Why are we talking about this? It seems a little bit, I don't know. It seems a little bit ad hoc, right? Like, well, what's the point of this thing? Why are we even talking about CDFs? Well, CDFs have a really, really interesting use, at least for illustrating something when we're talking about flows here. Notice another way to think about this CDF is a way to map some distribution, this p theta, to a uniform distribution. Now, I'm a little bit, I think it's a little bit unfortunate that we have 0 to 1 on the x-axis and 0 to 1 on the y-axis. It makes, to my mind, it makes me think, oh, well, maybe it's supposed to be that way or it has to be that way. But you could imagine that, on this axis, we could have, on the x-axis, it could have much larger bounds. Like it could be some uniform distribution. I don't know, uniform would be a terrible example. What would I think? Maybe a beta distribution or something, but also, no. I'm trying to think about something that would be outside of 0 to 1, but also not going off from like negative infinity to positive infinity. But anywho, I don't know. You could imagine having maybe a Gaussian mixture, and then we're just going to truncate this for the purpose of being able to see the interesting parts. But point being, this could go much below 0. It could go much above 1. But no matter what, you're starting at negative infinity, and you're coming along, and you're figuring out like what's the probability of a value up to this point, and then up to this point, and then up to this point, and up to this point. And so you're going to start carving that line out as you go along and as you accumulate more of that probability mass, until eventually you're going to start going off to positive infinity if it's a Gaussian, right? And it's going to sort of asymptote to 1. So you're never going to get above 1. And you're never going to be below 0, because if you're at negative infinity or way off that direction, there's no value less than that. There's no probability mass less than that. Go out to positive, there's no probability mass greater than that. So it has to start with 0 and end with 1. And well, if we go 0 to 1, if we consider this vertical axis to be, say, the uniform distribution, so let's say we sample uniformly from here, well, then we can then effectively sample from our original more complicated distribution, right? So just like a minute ago, we were going from the x-axis to the line and then mapping over. We were going from the x-axis up to the function and then mapping over to the y-axis. You could start with the y-axis and say, well, I'm going to randomly sample some value between 0 and 1 and say, oh, we get 0.62. And then I'm going to follow that over. I'm going to track over, track over, track over until I hit the function. And then I'm going to drop down to the x-axis. And then I've effectively, and I'm going to say, all right, we're going to take that value. And now I've effectively sampled from that original distribution. I know that seems a little bit wonky the first time you think about it, but what this does is it's effectively saying, I don't need to explicitly know this complicated distribution. I don't have to know it analytically. I don't need to be able to write it down. All I need to know is how to turn a uniform distribution into it. So that's what this CDF is doing. This CDF is mapping, in a sense, the uniform distribution to whatever this other distribution in question is. Does that make sense?
So in other words, Go ahead, Sujit.
No, I thought that, the CDF, the benefit of the CDF over the PDF is that it's invertible because it's increasingly monotonically, right? So you will never map to 2 points from, right, from Z to X.
Well, so that is part of a benefit,
Right.
let's say, of the CDF. And in our case here with flows, right, they do have to be invertible. So that is very important.
Right.
You couldn't use a PDF, but so yes, that's true. That the PDF would not uniquely map to that y-axis. But once again, it's not really clear what's going, that y-axis would even correspond to anything, right? Because that y-axis was just a probability density, right? So that doesn't correspond to actual probabilities. That's just a measure of probability density. Here, what you actually have, that y-axis is actually a probability, right?
Yep.
Or you can kind of think about it this way.
So Jonathan, the concept here is that you can choose different distributions of probability on the y-axis, and this CDF allows you to go to a distribution which theoretically can be anything from -infinity to +infinity.
Right.
You can map probability onto any kind of original, or for lack of a better word, a different distribution, but choose a distribution on the y-axis. In this case, it is uniform, but it could be Gaussian, it could be a mix of Gaussians, whatever on the y-axis, and you can take that through the CDF to any other kind of distribution.
Mm-hmm. Yeah, I mean, I would stop and think for a second, like, what. So in this case, because for the CDF, it has to run from 0 to 1, right? So unless you do like a truncated Gaussian, I'm not sure that would work. But there is a question of, why would we do uniform between 0 and 1 instead of maybe beta or some other 0 to 1 bounded distribution? I think the idea here is, if you wanted to truly sample, what is it? So I guess we're getting kind of philosophical here, right? What does it mean to sample from a distribution? Right. So if you have a Gaussian, or let's say you have some very complex distribution, I mean, if you wanted to sample from some particular region of it, I guess you could put a different distribution on that y-axis.
But that would have bias, though.
Right. And so that's I think that's the idea behind having a uniform on that y-axis. Is it's literally it's randomly sampling from the entire space for that complex distribution. So like this could be your data distribution on the x-axis, and you don't even know what it looks like, but this CDF is then mapping 0 to 1 onto it, right? So if you use uniform, then that's true. Anywhere in that entire distribution, you're basically trying to sample, like you say, unbiased sample from anywhere in that distribution. So yeah, so it would be interesting. I'm not sure when you would use a different distribution for that 0 to 1, but yeah. So I think the key point here is this allows us this gives us a way to sample from a really complicated distribution. Like there's kind of like 3 components, right? There's some distribution we can sample from. There's some distribution we want to sample from. And then we have some way to link the two, one way to map from one to the other and back. And so even if you don't have one of those pieces, you can hopefully recover it. Right? There's enough information in 2 of the 3 pieces to recover the other.
Yeah, this is cool. Very nice.
Awesome. Cool. Thanks, guys. And then here we go. So CDF can turn any density into a uniform. So we can go from X to U, and we can go from Z to U. We can go from X to U to Z. We could go X to U to Z to U to W to U. So this kind of shows you that, you can just go from one to the other as long as you have that, invertible differentiable property. Right? So then the question is, how complicated can we get here? So this is cool. This is a nice little proof. We can turn any smooth PX into any smooth PZ. But yeah. So let's see where this goes. So jumping into, so there's this really cool overview paper. I'm going to post this one as well. I like this one. It's pretty dense in parts, but it was a very helpful overview. So what is a normalizing flow? So normalizing flow is a transformation of a simple probability distribution, like a standard normal, into a more complex distribution using a sequence of invertible and differentiable mappings. Right, so back to normalizing flow. So normalizing, make sure everything stays normalized. Flow, sequence of invertible differentiable mappings. The big question though is, how do we do this? Right. So the first thing we need to know is, like, how do we relate two distributions of random variables? So how do we establish this relationship? So I apologize that I'm going to be jumping back a little bit back and forth between Y's and X's, and I've tried my best to smooth out the notation across all of these different sources. Everybody seems to have their different way they like to think about these things. But hopefully this makes sense. But if you see a mistake or if anything doesn't make sense, just jump in and be like, hey, what's that? Because I make, once again, everything here comes with a grain of salt. I make no guarantees of perfection. So yeah, so what we have here is our change of variables equation. Right? So we can relate our target distribution Y to our base distribution Z. And you can see the generative direction. He has two different terms here. I guess these are the common terms in this space, and normalizing and generative directions. Talks about one being like the push forward distribution. I think Z is the push forward distribution because that gets pushed forward through the network to generate your target distribution. So it was kind of helpful to actually see all these side by side. So let me think here. All right. So we have our Z distribution here, which is a function of Y, and then down here, this is kind of like, going back to the CDF, when we come down to this lower left plot, this is kind of showing how these two distributions relate to one another. So as you're going up here, this is basically mapping the target into the Z. So this is sort of the equivalent of that CDF, but it's not necessarily a CDF, right? I guess it would be a CDF if Z was uniform, but if Z is not uniform, then I guess it doesn't really qualify. But yeah, so this is just showing you how to go from the target distribution onto your base distribution. And you'll notice like this slope here, look at the far left side of the target distribution and the far left side of the base distribution. They're both very flat, kind of similar in that region, right? Well, you can see that as you're going up here, well, it's like 1-to-1. So it's the volume, basically it is mapping roughly the same amount of one distribution onto the same amount on the other. So this amount, let me see. It's my first time trying to explain this out loud. So what does it mean if that line was, say, at a 45-degree angle? And anyone care to throw something out there? So if the change in Z with respect to the change in Y was happening at a 45-degree angle, you saw that line going up at 45 degrees. Well, that would basically be, oh yeah, go ahead.
They're changing at the same rate is what I was going to say.
Right. Yeah, they're changing at the same rate, and so essentially it's basically a volume preserving transformation, Right, yeah, so the amount in one region is the same as the amount in another region. So the amount of X of Y space that you're turning into the amount of Z space, that amount is roughly the same. But then if it starts to, you know, say slope down a little bit, then that means we're now mapping more of Y onto Z. When it goes sharply upwards, then we're mapping, you know, I guess Y onto more of Z, right? So a little bit of Y side by side is getting mapped to a large swath of Z space. So this is kind of figuring out like how much of one distribution is going to you know, a particular part of the other distribution. So I figured this would be a difficult diagram to explain. I feel like it's one of those you just kind of have to look at and think about in your own way. But going back to the equation for a second, I guess I got a little bit ahead of myself. I just realized I had to talk about volume preservation and, you know, the Jacobian while I was also motivating, you know, what this term was, because you look at this and you say, okay, well, we've already by assumption said that Z is equal to some function of Y, right? That's up here. So we have Py of Y equals Pz of Z. So Pz of f of Y, because Z equals f of Y, then, you know, why in the world do we have this term? That can be a little bit confusing.
Normalizing, I think.
I mean,
looks
yeah,
like a
yeah.
determinant, yeah. Okay.
Yep. Yeah. So we do this term plays a very important role, but it's not immediate, or at least to me, it wasn't immediately clear why you would have this, right? So let's parse this out a little bit. This is kind of how I thought about it. So assume we have this invertible and differentiable mapping from Z to Y, and, you know, Y is going to be some parametric function of Z. Z is in RD, random variable with known intractable probability density function PZ. But here's the thing. We know that the probability mass must be conserved. Back to the, you know, big primary motivation behind all of this being normalizing. We want to conserve probability. What does it mean to conserve probability mass? Well, it means, you know, back to PZ of Z. So PZ is a density, right? That's the density for Z. The density is your probability mass per unit volume. So to turn density into mass, you multiply by this little bz. You've got this little infinitesimal mass gives you, this little infinitesimal volume multiplied by this density is going to give you a little infinitesimal mass. So let me repeat that again. So PZ is your probability mass per unit volume. DZ is an infinitesimal volume. So what you have is an infinitesimal volume multiplied by your mass per unit volume to get a little infinitesimal mass. And so all this is saying is an infinitesimal mass slice in the Z space must be equal to the corresponding infinitesimal mass slice in the Y space. And so that's kind of a key point there. So this probability mass must be conserved, and that's how we're saying it. So PZ dZ is PY dy. So I'm gonna be a little fast and loose in my notation here. Any real mathematicians out there might get mad at me for some of my some of what I'm doing here, but, you know, it's to be illustrative, right? So PZ dZ. So we're just going to plug in. What is Y? Y is f theta of Z. So it's going to, you know, we're assuming that Y, we can get Y using this parametric function of Z. All right. So P of f theta of Z, and then B f theta Z. Right. So we've just replaced Y with f theta Z. Now, all we're going to do is we're going to take that dz over to the other side. So now we have pz of z equals p of the mapping to y times this little df theta z dz. And then I just kind of wave my hands a little bit to finish it up here. But yeah, so there's that term, right? Basically, this is, in the way I was thinking about it, this is falling out of this, you know, this conservation of probability mass, So the Jacobian term then is just altering your density to ensure that that probability mass is conserved. And so going back to what you said a minute ago, where it's like, oh, they're changing at the same rate, right? And it's mapping the same amount onto the same amount. Well, what's going on here? If they're changing at the same rate, it just means the partial with respect to z of this f theta of z is 1. Well, there you go. Then that means that nothing changes. So if these two distributions are exactly the same, then, well, this partial derivative is going to be 1 everywhere. So it just maps on 1-to-1, no volume, no density alteration necessary. But if they are different, then there's going to be places where that derivative is going to change a little bit, and you have to map more or less onto more or less space of the other distribution. And so that's all that Jacobian term is doing. All it's doing is just, squishing down or pushing up on that probability density in a way that ensures that probability mass is conserved. All right, that was a bit. That was a lot. Is that good?
Yep. But that also means that so what we were seeing earlier on the CDF, right? And in this case, you have the base distribution, which corresponding to the previous chart, instead of it being uniform, is here a Gaussian, correct? So it seems to me, and correct me if I'm wrong, that the base distribution or the choice of distribution that you pick for the CDF for the mapping, the target is something that you don't know and that you're seeking to match. But the base could be any known desired distribution, such as uniform or Gaussian, correct?
Yeah. I mean, so the known or unknown part, I think determines. So I don't know here that it would necessarily have to be unknown. It was clearly to make this mapping here, they knew what the target distribution was and they knew what the base distribution was. So this is just this, the CDF, and now whatever we want to call this, I guess we'll just call this the flow, is just mapping one to the other. It's kind of like, it reminds me a little bit of vaguely of QQ plots, right? When you're checking to see, if your residuals are normally distributed. I don't know if that resonates with anybody, but it's basically saying like, I have a distribution. Does this other thing match? And I guess that gets back to what you said here. In the case where one of your distributions is unknown, you can kind of plot that and be like, how well am I corresponding to that? Actually, I think the QQ plot is a, who all is familiar with QQ plots?
I am. Yeah.
Okay. Yeah. I mean, isn't that kind of what's going on here? Like, correct me if I'm wrong. Once again, I was applied stats, not math stats. So, that's kind of what you've got here, right? Like if your let's say your target distribution Y was your data distribution, and then on the vertical axis you have say a normal distribution, then that's why you would hope that all those points are going to land along a straight line.
Right. Yeah.
Yeah. Same kind of thing. So, and likewise, if we did know both of them, we could also put both on. We could compare them, and you could, I guess, adjust it to figure out what that mapping would be. But yeah, I don't know if I answered the question. I hope that was close.
So yeah, I have a comment on this. So if you're familiar with calculus or remember some of your calculus, this is actually the change of variables formula. There's integrals missing. If you think of like P of Z has an integral over A, some area A, and then the P has integral over B, then it probably becomes more familiar. So all of this is just you're changing one variable to the other. You're just renaming, and there's the basic the chain rule kind of derivative that comes out of it. So, but if you remember calculus, that this is just the change of variables formula without the integrals being written. I think it's integrals go inside somewhere, but yeah.
Yeah, you're 100% correct. I mean, as I said, this was a little bit back to being a little loose with the notation. I was trying to be a little bit more, just a pedagogical way to kind of see it. But yes, no, you are 100% on the money there. Yep.
So it can sort of think of it as, we're just, if you're given, X and Y and you want to change it to theta, and you're just, it's the same thing. You're just transforming the variable from one notation to the other. But in order to do that, you have to have the derivative in there somehow, to make the integral work. So, but yeah. And so if remember from calculus, one of the tricks is the change of variable trick. So if that brings any memory, then that's just this formula. And if you ever did multivariate, then there's also the multivariate version of it. This has the Jacobian in it.
Yeah, and I confess, coming out of so I'm definitely familiar with it, and coming out of a physics background in undergrad, definitely did a fair bit of that. But I just remember the first time I saw it, like I guess I look at this and it's like, you can kind of think about math in a couple different ways. One is to think, oh, I'm just pushing symbols around, right? But I like to think like, what does this thing actually mean? What does it correspond to? I want to be able to point to some concept or something in my mind and be like, that's what this thing is, right? So this is kind of my attempt to rectify, square that, and say, so what is that? Oh, it's this spreading out of the mass, right? And so I'm trying to connect that a little bit to a physical concept.
Right. So your integral would probably go under also probability must be conserved, the formula under that. You put integrals on both sides, it kind of,
right.
It reads correctly, right? Yeah.
Yep. Indeed. Cool. All right.
Yeah, I think how the definition is where you're integrating over an interval for the representative. Maybe that like messes things up, but yeah, that's probably why there's more complication here. But
yeah, I mean, just part of the reason I didn't include the integral on the PZ and the PY part is, I was just trying to think about it in terms of like infinitesimals, right? So instead of like trying to integrate over like, oh, how much probabilities in this region, how much in the other. So yeah, you could totally slap the integral on there and say, okay, well, it's for any A to B on Z and C to D on Y or something, you could match those up. Yeah. Cool. Alrighty. So I just want to hit this one more time and just say, before moving on, note that we obtained an expression for p theta of Z, but we already know that, or sorry, p theta, that should have just been pz of Z. But we already know this distribution by our assumption, so we actually wanted an expression for p of y, right? Like under this whole assumption is we're starting with a tractable Z. Z is a tractable distribution. We already know it. We can write it down and we can sample from it. So we don't need it in terms of that distribution, right? But f theta is invertible, so no problem. Run through a similar thought process to before, and really you just plug and chug the other direction, and you just end up with this f theta inverse instead of f theta. And if you remember your linear algebra, then that the determinant of that f theta inverse, that term down there, the determinant of the inverse is the inverse of the determinant, right? So you can just pull that -1 outside. But yeah, so this shouldn't add too much more. Just wanted to clarify, right? So you can get an expression for either in terms of either, right? And so really what we want is presumably we have data, our y, right, in this case, and we have this mapping, which is invertible. Otherwise, we couldn't do this, and differentiable. And then we have pz. So this is the whatever this simple tractable known distribution is. So we want to be able to, in terms of data and that distribution, get an expression for our unknown distribution. So now we've rearranged that a little bit. So now we actually have an expression for the data distribution in terms of a tractable distribution and our differentiable and variable mapping and the data that we have, right? Cool. So yay. So we've got this expression for our unknown complex data density in terms of a known density. All we need to do is learn the mapping, right? How hard could that be? All right, so I was going to make change of variables a little bit more concrete. Sounds like everyone's pretty familiar with this, but I like this example that I found on another. So there's a corresponding class. I don't know if anybody else has come across this CS236 class at, I can't remember. Well, of course, one of these is Berkeley and the other is Stanford, and I never remember which one, I believe. But they had a cool little example in their slides. So, yeah. So Z is, oh, and I jumped ahead of myself. Darn. If Z is a uniform random variable, uniform on 0 to 2 with a density PZ, what is PZ of 1? And I just gave the answer away, unfortunately. So what would that be? So Z is uniform random, 0 to 2. So what is PZ of 1?
You just have to calculate the mass and then find the height. So
one thing we know, right? We know that the probability.
0.5. Yeah.
What?
0.5.
Yeah, it's going to be 1/2. It's just 1 over 2. Yeah. Cool. So now let's let x be equal to 4z and let p of x be its density. What's p of x of 4? So px of 4 is p of x equals 4. Is p of 4z equals 4. Let's plug it in. Pz of 1, which comes up to 1/2, right? Trick question. No. But hopefully you see why. If x is uniform on 0 to 8, then px of 4 must be 1/8. So what went wrong? What happened?
Just use the derivative there, right?
Sorry?
Well, we need to use the derivative, therefore it's 1/4 and multiply the half by the.
Right. Yep. We didn't do the change of variables for him.
Therefore 1/8. Right.
Yep. Bingo. Yeah. So we run back through that and say, all right, so using our change of variables formula, then we get z equals f inverse of x equals h of x equals x over 4. So that's the inverse, right? So then we go back through this and say px of 4 is then equal to pz of 4 over 4. And then the derivative of h is just always 1/4. And so we put all that together and we get pz of 1 times 1/4 is 1/2 times 1/4, which gives 1/8, which is what we were looking for. Yep. Cool. So yeah, so it's just a final little example to drive home the importance on that to anyone who is still wondering. So yeah. All right, let's talk about compositions of flows. So we can compose flows together, right? So we have like z, it doesn't just have to be f of x. We could have this f of k composed f of k minus 1, and we can go all the way out until we finally get down to f1 of x. And so what we now have is this. So let's say pz is equal to p theta of z sub k. So it's sort of trivial. By the time you come out of the network, hopefully it should be pz. So after the zkth layer, or after the kth layer, it should be correct. Okay, we go back a little bit and we're doing our change of variables formula along the way. We end up adding a term. So pz then is p theta of zk minus 1 times the Jacobian of partial fk with respect to zk minus 1. And this is just chain rule, right? Just keep on going, just keep on going, just keep on going. And eventually you're going to basically get a new Jacobian for each one of your transformations. And so all that's happening is that every single stage you're passing through is just a volume correction term, right? So back to the whole pushing down or pushing up on that probability density, as you're going through this sequence of transformations, it's, pushing up, pushing down, pushing up, pushing down, pushing up, pushing down, until you eventually get where you need to be, right? So that's really all you've got to keep track of, is just how much you need to push up or push down on that probability density at each stage. So that's all that Jacobian is doing. And so I liked this. So the Resende paper, this was one of the papers that sort of popularized normalizing flows. And here they show two examples. They talk about planar and radial flows, which I don't think we talked about in the lecture. But and apparently they're not very common. And they were even using this for a whole nother thing. They were actually using normalizing flows with VAEs. So they were using that for the basically using normalizing flows on the latent space, I think, to somehow create an exact. Once again, I can't speak on that because I don't know VAEs yet. So, but they were using this with VAEs, right? As I thought the graphics was pretty cool. So you can look at the top and say, we started with a unit Gaussian. So this is our starting distribution. You can see after just applying one planar flow, okay, after applying two, and then after applying this whole sequence of 10 of them, you can actually get something relatively complex. And then likewise, for this radial flow, you can see it can do something very similar. So you apply one, and you get a little bit of a change. You apply another, you get more of a change, and so forth and so on. And then down here with the uniform, I thought that was kind of interesting. See, after each flow seems to kind of cut it a little bit, right? So after one planar flow, you've got this one line. After two, you've got these two, and then after 10 of them, you've chopped the space up into this pretty complex distribution. And then there's another example with radial flows from a uniform. So, yep. All right, and then how do we train these? Well, it's just good old maximum likelihood estimation. So you're just maximizing that log likelihood. And all we got to do is plug in our change of variables formula. And we end up with this. And we can separate out that Jacobian term, just like this. And yeah, it's pretty straightforward. So basically, you just have this MLE, that you're just going to do MLE like you normally would, right? And then for every transformation, every little chain in that flow, every little link in that flow, you're going to add another Jacobian term, right? So yeah, that is about it. I'll pause here. Did anybody have any questions on the training?
Nope, sorry, on the color plots that you shared, it's just illustrative of mapping starting with a Gaussian or a uniform and then applying normalizing flows to try and show that if you do that, then you can pretty much get to any other kinds of distributions that you're trying to map to, right?
Yep.
That's kind of what this picture illustrates, that the normalizing flows, you can start with unit Gaussians or uniform and then get to fairly complex distribution, which is the underlying distribution that you try to map to.
Bingo. Yep. Yeah, I mean, that's a little reminiscent of sort of everything we do with neural nets, right? It's just a whole bunch of if you go old school with sigmoid, it's just a whole bunch of logistic regressions, right? So you stick enough of them together, eventually you can get something pretty complex.
Yeah, but I think the trick here is to go backwards as well, right? For flow models, right? So, once you have this complex thing, you want to go back or have some way of mapping back to the original.
Oh, right. Yeah. 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 So, I mean, yeah, once you have this very complex thing, then you can go back through the space and you can actually figure out, okay, what is the probability? What is my probability density for this image or this piece of text or what have you? So, yeah.
But that sort of stated differently, you would want to make some change in this uniform or unit Gaussian and see the effect of that change on the underlying distribution that you're trying to map to. Is that right? That is, you can kind of that you can make changes in this space, which is kind of the latent space, the uniform or the unit Gaussian space, which is much more complicated, and then go back and look at what that causes in the underlying distribution space that you're trying to map to.
Oh yeah, 100%.
Because that's what it enables you to do.
Yep. Yeah. On that note, I think you just set me up for the next slide. Was it the next slide I had? It's actually after sampling. So everyone, I guess, saw the sampling. Sampling by now, everyone kind of sees how that works, right? Just sample from Z, and then you can, push forward through the network to get your X, or push backward. Set that up. But yeah, to the point on being able to do things with the latent space. Okay, I don't know if everyone can see that then. I think that showed up in a separate window.
Yeah, we can't see it.
Let me try this again. There we go. Okay, can you see it now?
Yep. Yeah.
Awesome. So yeah, if anybody got into the second part, you saw them talk a little bit about glow. I think they actually talked about that in one of the earlier lectures too. And back to being able to do really cool things with latent space, right? So because you have that exact mapping, you can actually extract interesting things from your latent space. So you can say, okay, well, I've got this whole collection of pictures that look like they're smiling, and this whole collection of pictures that look like they're, frowning or not smiling or whatever, right? And you can sort of figure out the direction to go from one group of pictures to the other. And once you have that, then you can play around with it and say, okay, well, I want to, take this image, send it through the network, basically figure out, the corresponding point in the latent space. Then I'm going to shift that point by whatever the thing is that I'm interested in, some amount, and then run it back through to see what I get. So we take this original picture and we can make her frown, or at least not smile, make the smile bigger, younger, older. I actually like the Jeff Hinton one. I think Jeff Hinton worked pretty well here. So make Jeff smile, make him frown, make him young. It shouldn't change too much. He looks pretty good with the beard, though. There we go. And a smile. So yeah. So yeah, back to what you're saying, like the cool stuff you can do, like once you actually have direct access to that latent space, then you can actually start to poke it and prod it and learn some interesting things. So there's that example. Where was the one where they change? Yeah, there you go. Changing the author of the paper, or one of the authors of the paper, into various celebrities. And it's interesting to see how even those images in between kind of look realistic. It's not like it just goes through this weird disjoint phase and then you recover something that looks real. It's like more or less every image along the way during that transformation looks kind of like a person, right? So I think this definitely qualifies under that category of having a meaningful latent space. Yep. I think they talked about it down here. And there you go. Since flow-based models have a perfect encoder, you can encode inputs and compute the average latent vector of the inputs with and without the attribute. The vector direction between the two can then be used to manipulate an arbitrary input towards that attribute. So, yeah. So I'm going to hop back on the slides. I actually really only had one more slide, and if you want, we can jump over to the lecture slides. So I didn't quite get this totally finished, but this was about where I wanted to stop. So just an interesting point about expressiveness too, right? So what we've seen is we can do exact sampling, we can do exact inference, and then we just saw that we can actually poke around with the latent space. So we have a meaningful latent space. If you remember all the way back on that first slide, the fourth property we're interested in, or the fourth property I've not mentioned so far that we're interested in, was expressiveness, right? No, that wasn't it. That was one of the other properties. So apologies, I messed up there. But expressiveness is certainly something we're interested in. Right? So it has a meaningful latent space. We've got exact sampling, we've got exact inference, and turns out that some of these architectures have actually been proven to be universal. Right? So for several autoregressive flows, the universality property has been proven. In that paper I mentioned that has the good overview, they have a proof, they replicate the proof in there. But basically, this can learn any target density to any required precision given sufficient capacity and data. And that's just, to me, that's awesome. Especially as opposed to like some of the other generative models. Like this, I don't know, this just seems like you get to eat your cake and have it too, right? Like if you think about with simple feed forward, we all know that the sigmoid network here, you've got a universality property there. I think it's been proven for ReLU too. So these discriminative architectures, we've seen universality proven, but it's kind of cool to see that we also have universality for these generative architectures too. So yeah, that's about all I've got for today. I was going to hit on all kinds of different architectures. So we were going to touch on inverse autoregressive flow, nice, real MVP, Glow, Flow++, and Fjord. Yeah, if anybody has any more questions or you want to jump over to the other slides, we can do that as well.
That is great. Thanks a lot, Jonathan. That was awesome to go through kind of the distilled version of it, but with a lot of insight into what we're actually doing.
Thank you. And actually, I'm going to go ahead and pull my this screen back up, and I'll pull the slides up just to refresh. So if anybody did have questions on here, I didn't touch on this mixture of Gaussians thing. I didn't see that as like terribly relevant or terribly important here. The big point he made with this was sampling for really high dimensional spaces and really complex concepts. You can't, simple models like these Gaussian mixtures just don't work well, right? All you end up doing is adding like salt and pepper noise, right? So, but, yeah.
Yeah, I've done toy problems with mixtures of Gaussians, and they seem to work pretty well, but maybe not in high dimensions, right? Maybe that's the problem there.
Yeah, I think the point with this one is like you see what happens with these corgis, right? Like if we think about concepts, like if you think about all the different ways you can orient, a dog or the different kinds of things that would correspond to a dog, it seems like there's a whole lot of them. But if you actually think about how many possible ways you can, permute the values of the pixels in that image, that it's so much vastly higher. It's like it's extremely sparse, right? And the next picture of a dog isn't just a bump away from what the current picture of a dog is, right?
Yeah.
Like there have to be these wholesale changes, but they have to be changed in very specific ways. So you can't just permute or add a little perturbation about some cluster center, right?
Yeah.
Like he says, you basically have, it's almost like I guess it's almost like a bunch of islands, right? Like all these different pictures almost like form islands in this space because it's so sparsely populated.
Yeah, in the previous autoregressive, I think he touched on this Gaussian mixtures, but there I believe like he uses it to model. If I recall, it was like a mixture of 4 Gaussians, but then again to model a fairly narrow or maybe not a high dimensional space.
Mm-hmm. Yeah, I think
autoregressive lecture he does that.
Yeah, I think the key there would be that everything, all of those values would somehow be meaningful, right? Like if you're looking like that one-dimensional case up here, there's like some assumption that those are actually meaningful values that you could get. Whereas like with these images, the meaningful settings are not right next to one another in that space, right? But yeah, let's see. Yeah, I don't know that there's as much else we need to touch on here. Yep, this is what we're going to get into next time. All right, cool. Any more questions?
Nope, great foundations.
Yeah, very, very insightful. And, I think I got more out of your stuff than actually reading this thing by myself. So,
awesome. Yeah. Thank you. And I really appreciate the discussion too. Like it's, I do think we all tend to be quiet sometimes. And I don't know, for me, sometimes it's because I've not had my coffee, and other times it's because honestly, I'm just not really sure what's going on.
Yeah.
Or what I could contribute. So I was hoping to make it a little bit more engaging.
Yeah, definitely did. Thanks.
Awesome.
Yeah, really interesting. Yeah. No, thanks for putting together the customized presentation. Helped a lot from just looking at the sort of original slides and the original lecture.
Yeah, I was thinking the same. You started at the beginning, and the course slides don't hit the beginning until slide 20 for some reason. But maybe they had a different background during that semester. I don't know.
Yeah, that's possible. Yeah.
The week before maybe made sense.
Yeah, thanks. Yeah, I noticed going through all these different materials, everybody presents it differently. Some people start with change of variables and talking about Jacobians and what's the geometry here, and other people are a little bit more applied and empirical and jump straight into examples. And yeah, I guess it depends on your background.
Yeah, but also I think the exposure to approaching it differently triggers better insights, because the same thing some concepts seem to jump at you easier for lack of a better terminology, in one flow versus in a different flow of presentation. So I think yours helped in many ways.
Thank you.
And when you get the time, if you can also post the references,
Yes.
just even in saying that would be great. I'll compile them as well and post Google Drive or
100%. I'll drop that. I'll drop that in the chat here in a little bit. And go back through and
great.
Clean up and make sure my references are on point.
Awesome. Thanks a lot, Jonathan. Any other questions?
Oh, I just missed it. What are we starting with next time?
Oh, next time is going to be starting with inverse autoregressive flow, autoregressive flow. I guess I would include that masked autoregressive flow, and then the nice real MVP architectures, and then the more advanced, the Flow++, Glow, and Fjord.
Sounds good. Thank you.
Yep.
Okay, great. That was excellent. Thanks a lot, Jonathan. Thanks everybody for joining. We'll meet again a week from today.
Thanks, Jonathan.
Yeah, thanks, Jonathan. See you next week.